can see it right here.
All right, you ready? Okay. So, we are here at the Cuyahoga River, and here's Standing Rock. And how many of you have been to Standing Rock or seen Standing Rock before? You? Okay, so most of you, but a few of you haven't. Lifelong residents of Kent. It's okay. When I got here, everyone's like, "Oh, you need to go see Standing Rock," and I was like, "Oh, sounds like a rock standing." But it's actually a piece of historical evidence of what happened to this river about 10, 15,000 years ago. So what was going on in northeast Ohio about 10,000, 15,000 years ago? You wouldn't know? What's that? Not war. There were glaciers, that's right. And so this was covered by ice. And we were on, where we are now, was the edge of one of the lobes of the Wisconsin Glacier. It's called the Grand River Lobe. And what happened was that glacier had come from the north and plowed over everything. And then as the climate changed around and it got a little bit warmer, the glacier began to retreat because it was melting and shrinking, and it left behind this giant boulder right in the middle of the Cuyahoga River. Now, the Cuyahoga River used to be a just plain old north-south running affair, but the glacier, as it retreated, carved a new channel for it, and so it gets its crooked shape, which is kind of like a V shape, where it starts upstream that direction, I think about 40 miles, 30 miles up that way, up in, I believe, Cuyahoga County. And there's East Branch and West Branch of the Cuyahoga River. You may have been to, there's a park up there where it joins. And then comes down through Manaway, and which is where Crestwood High School is. And then to Kent, continues on down through Kent, and around it starts to curve a little bit and goes toward Cuyahoga Falls, where there used to be a natural falls, and then they put in a big dam, and that's where the gorge is. If any of you have ever been to the park, the gorge, and there's that big lake in front of it, that's not a natural lake, that's because of the dam that's there. And then it takes a sharp turn northward and heads pretty much due north up through Peninsula and Independence and all the way through Cleveland, where it empties into Lake Erie. And so all this rainwater that falls on Kent and on that side of the river will drain into the Cuyahoga River and then eventually end up in Lake Erie. The interesting thing is that we're on the edge of a major watershed divide. If you go to the other side of Ravenna, so you're on the east side of Ravenna, like where that giant eagle is past downtown, that rainwater that falls there actually goes down into the Mahoning River and eventually to the Ohio River and eventually to the Mississippi and into the Gulf of Mexico. So we're right on the edge. Rain in Kent goes to Lake Erie. Rain in the east side of Ravenna goes to the Gulf of Mexico. Yeah, so we're right on the edge of that. We're also on another historical border. Back in the late 1700s, when Moses Cleveland was doing his surveying of the area, this was the original dividing line for the United States of America. You are right now in what would have been Iroquois or Indian territory. So the Iroquois Indians owned this part. Across the river there was the United States of America back in the late 1700s. And of course, we violated that treaty and moved into this land anyway, but right now you would be in foreign territory back in the late 1700s. So this used to be the dividing line of the United States, and we're on the other side of it. Before the white men came, this Standing Rock also served as a meeting place for the Iroquois Indian tribal elders. They would climb to the rock and have their meeting. It was like their conference room. And you can see that now we have, there's a Canada goose nesting on top of it, and yeah, it'll have little goose babies, goslings pretty soon. So why are we down here with the chemistry class? Well, the Cuyahoga River's been through a lot, and a lot of it's not good. There have been instances in the past where down in Cleveland, not this part is called the Middle Cuyahoga. Farther upstream is the Upper Cuyahoga, when it's really more like large streams. And then past Cuyahoga Falls, that runs through Akron, that's the Lower Cuyahoga. And then into the city of Cleveland, where it was dredged out. That part actually caught on fire about 14 or 15 times. And that sparked the whole modern environmental movement as we know it today. It was one of the things that led to the founding of Earth Day, which was yesterday, when this river, not this part, but farther downstream, caught on fire in June of 1969. And I think it was June 22nd, but I can't remember the exact date. Anyway, it was at night. It was actually not a huge fire, but what happened was the fire that occurred was written up in a Time magazine article that happened to also be in the issue where Senator Kennedy had driven off of a bridge with a young female intern in the passenger seat and killed her, and he ran from the scene because he was drunk at the time, which we found out later. And so that was what occurred in the incident at Chappaquiddick, and that was the highest selling issue of Time magazine ever. And in it was an article about the decay of American cities, including Cleveland and its Cuyahoga River, which they said was so toxic that it actually caught on fire, and that if you fell into it, you would not drown, but you would decay. That upset a lot of people, and that led to the push for the first Earth Day, the founding of the Environmental Protection Agency, the Clean Water Act. These things, there is a direct cause from the what happened with this river, the effect of environmental awareness as we know it today. So this is historically, there's only 17 heritage rivers in the United States, and this is one of them. So this river is incredibly important, not because it's great for shipping or trafficking here, although it is important for shipping up in Cleveland, but because it's so historically important. And in fact, what we know about water quality around the world, you can tie back to what we learned first in trying to clean up the Cuyahoga River. And that's why we're down here today, because you guys have been learning about solutions, things dissolved in water or in other solvents, and you are going to measure some of those things in the river. So you have some sheets. So let's take a look at your sheet on your clipboard. And on this sheet, there's a series of boxes you're going to fill in based on the data you find. First of all, we have to come up with a site name. If you were to name this site where we are now, what would you call this? The Rock? Wasn't that a movie? Or a wrestler? Yeah, Standing Rock. Why don't we say Standing Rock on the Cuyahoga River? And one thing that scientists love to have is GPS coordinates, which is exactly where we are on the planet in latitude and longitude. And Brittany, I think you have the GPS, right? Can you tell us the latitude? 41.16619. Okay, so 41.16619, and that's degrees north of the equator. And we went up to 90 degrees, that'd be the North Pole. If we were down to 0 degrees, that would be the equator itself. And then the longitude tells us how far east or west we are of Greenwich, England. So what's the longitude?
Negative 81.35055.
All right, so 81.35. Did you say 055? Yeah, 055. And that's degrees west, or you can say it's negative. West and negative mean the same thing in longitude and latitude. Okay, what date is it? What's today's date? 23rd, so it's 4/23/2013. Very important if you are doing field work out doing science outside that you say what date it is, and also what time is it? Anyone know the time? Like 9:45, 9:30? 9:35? Okay, good. That gives us plenty of time. And if we were going to do a whole write-up, we would write down the weather, etc. We do have the air temperature, and I think, Brittany, you have that.
17.3 degrees Celsius.
Okay, so that would be 17.3 degrees Celsius is the air temperature. What's the air pressure right now on your barometer?
0.06.
0.06? Uh-oh. That doesn't sound right.
Oh, that's in kilopascals. Yeah, no, we got to change it. Hang on a second.
That's not right either. We have to fix that one. There we go. It was just hanging slide. Hang on a second on air pressure. We'll get this fixed for you. All right, there we go. So Brittany's got the air pressure in barometric units of millimeters of mercury, which is what we'll need for later. And Brittany, what is that?
748.7.
Okay, so 749, and it's MM, capital HG. And then water temperature, we'll get that in a minute. So you guys have a series of probes that we're going to use to measure the quality of the water, and your results will give us a grade for each one of them. So for example, who has a nitrate probe? Look on the side, your probe should say nitrate. I think two of you, at least. Okay, so there's one. Anyone else have nitrates? Is that the only one? Cheyenne, we're going to rely on you alone. You don't have nitrates?
I don't think so. It says...
it say NO3?
No.
All right, so we got one nitrate. That's fine. So what's going to happen is Cheyenne's going to be our nitrate person here. She's going to take this probe and put it down in the water, and it's going to give her a reading, and then we're going to use graphs to interpret how good that reading is. Because it comes back and says 1 milligram per liter, which is measurement of concentration, you don't know what that is. You don't know if that's good or bad. And so I'm going to walk you guys through those probes as we go. So some of them are very easy. Who's got temperature? Who's got temperature? It's just a steel probe. It says it on the side. You got temperature? You got temperature. All right, so you ladies, yours are pretty easy. What you need to do is measure it at a site up here and then walk down a bit and measure the temperature down there. Make sure that the metal is submerged, but not all the way to the handle. You need 2 readings, one here and one there. So go ahead and get to work, okay? Just go down and tell us the temperature. Make sure it's in degrees Celsius. Okay, who has conductivity? Anybody else have conductivity? That's a little box. You got it? It's got a little box on it. It says on the side of the probe what it is. Conductivity. We got 1. Okay, so yours is also easy. You can actually go with Bree if you want. You just put it in the water and write down what it tells you. Okay? That's a very straightforward probe. Who has pH? We've got 2 pH. Okay, so we're going to learn more about pH pretty soon when we talk about acids and bases. This probe is stored in what's called a buffer solution that's supposed to, keep the probe happy. When you unscrew it here, you can't just yank that out. You'll damage the probe. That's true for most of them. You're going to unscrew that, and this cap has an acid in it. It's not a bad acid, but we don't want to pour it in the river because it's polluting. Okay, so you're going to put that into the river. You're going to swirl around gently until it stabilizes and tell us what the pH of the river water is. Okay, so go ahead and you can do that right down here where it's easy to get to. Okay, let's see. Turbidity, you guys stay over there because yours is a little different. And then you have what? Dissolved oxygen? You have dissolved oxygen? Okay, you have the pickiest probes. And you have nitrates, right, Chan? Mm-hmm. And what do you have? Dissolved oxygen?
I know, right? Nitrates.
All right, come here because you guys it's all the same. Come here. Cheyenne, you too. All right, so the DO probes have distilled water in them, so it's not a big deal if those get out. These, yes, he says nitrate. These have a sodium nitrate solution in it that we also don't want to dump out. It's not dangerous or anything. Well, don't do that. But we don't want to dump it because then I have to make more. So again, don't yank out the probe. You'll damage the membrane. So you're going to unscrew the cap here and then just shake it off. And you're going to put it in the water and you're going to make sure it's submerged up to about the cap here, maybe a little higher. The DO probes have a metal button on the side. Yours do too, but it's farther down, or it's closer to the tip. That needs to be submerged as well. So just get it in there, swirl it around, wait until it stabilizes. DO is a little picky, so it may never fully stabilize, but do your best. Nitrate, it's not a big deal. Just don't dump it. Put it down there, swirl it around, get your reading. Okay, and put it back in there when you're done. And then so go get your reading and come on back when you're done. All right, turbidity. What yours is measuring is how cloudy the river water is. So you can actually leave everything here except for this vial inside. Now your lid got broken off some years ago, so you have to put that back on. So don't lose that because that gets lost every now and then. I have to come find it again. And you're going to fill this up to the line, and you guys know the meniscus, the curve in the water when in the graduated cylinder. Well, it does that here. You just want to make sure that the bottom of the meniscus is at the line. And then when you bring it back, cap it. Don't shake it up or anything because that'll add air bubbles, which will artificially increase your cloudiness or turbidity. And then you're going to match up the triangles here and here, and then put that on, and then you're going to let it sit and watch this reading to see if it stabilizes. And hopefully it will be normal in about a minute or so. So yours is actually pretty easy. It's just involves some patience. So go ahead and set your stuff down and take your vial down, and then just when you're getting the reading, the water out of the river, just don't fall in. Okay? That way is a little steep, although you can. I recommend going that way. Okay. So you've done this before, so you remember this from last year, right? Okay, good. So when we get back up, I'll make sure you guys get the sheets and you can get data from another group. Okay? So, not a big deal. Yes? Well, like the rope there? Oh, are you talking about Brady's Leap? I think that's farther up, if memory serves, where somebody was running from an Indian tribe and jumped over
Yeah, I think Brady's Leap is up that way a little bit.
I thought it was
That would be pretty monumental to jump that far. Now, I've been down here before where it's been flooded. We had some flooding like 2 years ago, and it was like 2/3 of the rock was covered. You can only see the very top of it. So the water can come up pretty high. So that's, you know, that's what it's doing. It's draining. Okay, so you've got
Do I have to
data?
do it twice or something?
No, just one.
What do you have to write down twice?
Okay,
There's a part two test. Yeah.
right. Well, we need water temperature, so just pick whichever one you did first. Yeah, that helps. All right, and then did you get your data?
No, I actually want to talk to you really quick.
Okay.
Richard's thing, and it has like critical battery power, so it's like
Oh.
shutting off.
Okay.
Also, inside of
Don't worry about that.
Okay.
Yeah,
no?
don't worry about that.
It's okay.
It's
Alright,
fine.
I just want to make sure.
Yeah. Blame Lambert. All right. You
I'll
got
be back.
battery issues? Did it shut out? It shut off. Oh no. All right, here, trade me. Oh, actually, yeah, let's just do that because you got your number, right?
Yeah.
And you wrote it down? Yeah. Conductivity is the easiest measurement ever. You lucked out. All right. Let's make sure pH comes up. Great. And it's the buffer of 4, so we're good. So this one just needs to be charged.
So 201's like normal?
Well, that's what we don't know. Okay, so here's what we're going to do. And then, Megan, if you want to show people how to do this too, since you remember from last year, remember the charts, the graphs?
Yeah.
You know how to do this. All right, so conductivity is total dissolved solids. And you got 201, which is right at 200, so that's how many milligrams per liter. So all you're going to do is you're going to take your pencil and draw the straightest line possible. And I like to use like just another sheet of paper as a ruler. And you're going to draw that up to the intercept of this curve. Then from there, because it looks like it intercepts around right there, right? Then you're just going to draw a line over. Do you remember doing this for half-lives? When we were looking at how many half-lives?
Since I was absent for half-lives, I never really understood.
Oh no, okay, well this is good that we're going over this because that'll be on your exam, and it's the exact same thing. So in half-lives it would be the amount of time has passed and what percentage of radioactive material remains. Here it's how concentrated it is and what is your Q value. And the Q value is kind of like a grade. In other words, how good is it? And if you're taking a test, 100 would be awesome and a 0 would be terrible. So that's just what we're doing. So we're going to go up to the line here and then draw over. And what would you think that would be?
Probably around 70 something, like under 75.
Yeah, so under 75.
So, pretty good.
Well, give it a number.
73.
73, I like it. Okay, so you're going to write down 73 for your Q value there with your pencil. Okay? And then as more people get data, you're going to do that for the other ones. Okay, so you have numbers.
They said exactly the same thing.
Oh, that's fantastic. That means you had a temperature change of 0. That means there's no thermal pollution in your the water that you measured. That's typically the case, especially when it's colder. So that's great. We're going to need that temperature, by the way, that you took. That's going to be critical for dissolved oxygen. Dissolved oxygen is the hardest measurement to make, so I feel sorry for Josh and was it Cheyenne? No, she had nitrate. Whoever the other person was that had DO, that's not going to be fun. So you guys, you have an easy one for temperature change. So go ahead and tell Aaron what you got.
For the temperature change or
Yeah, for both.
the temperature 12.4. I see.
Mm-hmm.
Yeah.
You'll need that.
And the
You guys got numbers?
Yeah, but they're really different.
Okay. That could be because the samples you took are different. Probably not that. It's probably likely that they just need to be calibrated. Yours is 32. Yours is 8.8. Huh, those are a little different, aren't they? Okay. Did you make sure the outside was wiped off and it's not like smeared or anything? There are no fingerprints on the outside of the vial.
201.
Okay. Check to make sure the vial's clean. You might need to, like, use your sleeve or something to clean it off. Okay, and you have a temperature change of 0. So what you'll do is on this graph, you're going to look up the temperature change graph, and you'll see that down here on the x-axis for all of these graphs is what you actually measured. Then on the y-axis here, this is your Q value, and that's kind of like the grade of your reading. How good is your reading? 100 would be an A+, a perfect. A 0 would be an F. So that's what we're going to try to find. You can see 0 here. 0 is an easy one because it peaks up here. What do you think that peak is? Yeah, about 93, okay? And that's an A, isn't it? So for the Q value for temperature, you write 93.
Oh, you're
You might have been looking at a different graph. It is confusing. There are 6 graphs. There's also a way to do water quality index with 9 readings. We're not going to worry about doing that. That's a little bit too intense.
Alright,
Okay, so you have numbers.
Yeah, mine went down.
Yeah, I don't know what the Q value is.
Okay, and you had nitrate. Sweet. Okay, so Q value. I'll show you how you guys do this for each one. So this is your data, and like you said, you don't really know what that means. Is that a good reading or a bad reading? So on the graph, there's a graph for each of these, and you had pH. So on the x-axis, do you remember doing radioactive decay, and you looked at like how long something had been, and the x-axis or the y-axis told you what percentage was left? It's the same thing. We're going to go here to what'd you say, 6.3? So put a little notch at 6.3 there. Okay. You're going to draw a line up until it intercepts with the curve. You can do it literally or visually, but you get the idea. And then you see it where it almost exactly hits 60 there. So that's your Q value. So if we were to call that, a grade, that's like, a D minus. Really, in this, it's average. But we're going to put 60 down for your Q value, and then you'll share that with her. Okay, so you got 1. So you can see that's pretty high. That's like, what would you say that number is on the y-axis there? Yeah. So 97. I like it. All right, so flip it back over. And we're going to put down 97 for your Q value. That's an excellent nitrates reading. Nitrates are a sign of fertilizer and fertilizer runoff, and also they can also be related to food, like from cows, because they're high in nitrates. So then share your numbers and get numbers from them. Okay? So collaborate scientifically. Is it 7? Okay. Now, what you're measuring here is the suspended solids, and if you remember from when we learned about solutions, colloids, and suspensions settle. They'll eventually settle out. So as you let this run, you're going to see that the number will get smaller and smaller. So we're looking for, after about a minute, what is it? And then we just, it'll eventually go down to close to 0. So we're going to go with, like 7.5, 8? You had like 8 something before, so I like 8. 8's a good number. And you have, what, like 23? Okay, right before the screen turned off. Okay, so great. You guys are done with those. Go ahead and get your clipboard up. Okay, so you're going to go with your number, and so that's turbidity. So you're going to write down 23, and that NTU stands for like nephrotic turbidity units, which don't even worry about that. And then yours is 8. And what it really is, the reason your probe is different is it has a little light in it, a little LED light that shines light through the vial, and on the other side there's a photosensor that tells you how much light got through. So that's really what the turbidity is. Okay, so this is a measurement of cloudiness. So is this a good value, a bad value? Well, what you do is on the back here, your turbidity graph, which is total suspended solids. On the x-axis, ignore this one with inches, this second x-axis here of 0, 10, 20, 30, those are your NTUs, and you're going to make a little notch for what you had. So you had, what, 23, George? Yeah. Okay, and you had 8, so it's between 0 and 10 there, so make a little notch. And just like on the radioactive decay curve, we're going to draw a line up here until it intercepts with our curve. Okay, and then draw a line over to your y-axis. So see where the intercept is? And then that tells you your Q, and that tells you how good it is. So 100 would be perfect and awesome, 0 would be a major fail. So what for your reading, what did you get? About 58, and for your reading, you got what? 80. Okay, and that's you're gonna see that that's all going to average out when we do that. So keep your numbers and write down your Q value here, because that's what we really need. We need the Q value. All right, you got data?
George.
And then once you got data, share with everybody else what you have. All right, how'd you do? You don't know? What'd you get? Boom. No, you were recording. Oh, okay. Well, the high value there, it looks like when it started to flatten out, it was like 2.2. So let's go with that. It's a little on the low side. I'm a little surprised. We may need to calibrate that. And then you did nitrates, right?
Yeah.
Okay. What is going on here? Okay, I got a second. Let's look at the table.
Mr. Carmen,
Yeah.
me and Michelle got like 2 completely different readings.
Okay, that's fine. That's why we take them with multiple probes so we can average them out.
Okay.
Right? Looks like you got a lot of 1.4s. So let's go with 1.4 for your nitrate reading. Okay? What did you get for
Like I got
DO?
0.8.
0.8. Oh, that's not good. Yeah, this probe is having problems. Okay, so
Yeah,
we're
she
gonna.
got like 2.0, I think.
Yeah, so let's go with Michelle's reading. I think this
Okay.
probe's having problems today.
Okay, that's
So just write that down for your dissolved oxygen.
Yeah, because I was like, we got 2 completely different readings.
It's like reading this, it's like
That's
good.
cool. So for Dio, you're gonna write down 2.2, and then you got your 1.4, and then Michelle got 2.2 in milligrams per liter. Dissolved oxygen is not really fun to measure, so we will measure that. We'll work on that together as a class. So for those of you who just came back from doing your readings, again, what you're going to do is, so you did nitrates, for example, you're going to take your data, you're going to find the graph that matches up with your data and look at the x-axis. And so you had, what, 1.4?
Yeah.
All right, so what you'll do is you'll put a little notch on the x-axis for your reading. So I'm going to make a little notch there for 1.4. Then you draw a line up from the x-axis. You did the same thing with radioactive decay. You're going to draw a line up here until it intercepts with your curve. And I probably could have drawn a better line, but you get the idea. And then once it intercepts with your curve, draw over to your y-axis to tell you what your reading is, and that will be your Q value. And your Q value for your reading is how good is it? It's a grade. 100 would be a perfect score on a quiz or a test, right? Well, 100 in here would be a perfect score for data that you took in the river. So we're taking physical information, a concentration of something, and we're turning it into numbers that we can manipulate to tell us, is it good or not? And so that's the purpose of this, of doing this conversion. So what would you think that Q value would be? Yeah, so 90 what? It's not 90. 92? Yeah, that's good. All right, so write that down for your Q value for nitrates. Now share your numbers. You should have numbers for everything except for the Q value for dissolved oxygen because that's a pain, and I'm going to walk you through that. We might have to wait until we're back in class for that one because that involves rulers.
We've got 10 minutes.
We got 10 minutes? Okay, then we need to start heading back. All right, so before we have everything done, and we don't have dissolved oxygen yet, which is fine, please make sure your name is on these at the top because I'll hang on to them for you so you don't lose them. So far, gut feeling, where do you think this is going to end up? Do you think we're going to end up in the excellent range, good, average? What do you,
Average.
average? Or, I hear one person thinking it's good. All right, so we'll see. We're going to do all these measurements when we're back in the classroom tomorrow. Okay, so let's head on back so we're not late.